Bing bongy bong, bing bongy bong. This is Joe, the bearded historian. He'll tell you an interesting story. Be careful of his soldiers, they can be brats. This is Angel, she's an entity. She'll cause chaos and plant her hands at you. This is Sue, she likes spirits, not the alcohol. She's the reason this channel exists. This is David, he likes fire trucks. He's here occasionally. Bing bongy bong, bing bongy bong, bing bongy bong. We preserve his story.
Welcome to Wayback Wednesday, where Joe's going to ramble about an explosion that happened because, humans are silly. Before that, we have got a race. I've chosen, what did I choose? Oh yeah, robots. Because, well, why not? Apocalypse and stuff. Are you ready? Here we go. Oh, also, I am still working on the year in review. Hopefully it will be up on Friday. And we've reached 1,600 again, so I've got to work on that. Hopefully that will be next week. I'm aiming for Monday, but we'll see. Ready? Here we go. Shout out time. Here's a shout out just for you. You support me, so I support you. This shout out is for a friend. Let's see who it is today. Start. Oh, for Pete's sakes. Okay, there we go. Alright, we got Shesoul, Heather, Pete, Gypsy, Teza, Turtle, Lucia, Gypsy, Lashes, Jared, Old Fart, Carter, Hiking Ontario, Gen X, Sheen Sean, Turtle, Lashes, Jamaica, South Mountain Man, Stace, Embarkment, Sweet Pea, Fine, Cheap, Rich Cat, Luscious is currently in the lead. There's Really Haunted. Here comes She Stole from the Back. Ooh, it looks like it's going to be Abandoned. Alright, yeah. Alright, Abandoned and Forgotten Wells is video documentation of old metal lines in mid-Wales for future generations to see, set back in time, where miners once worked. So, as you can guess, it's a lot of mines, a lot of underground, a lot of exploring. So if you like that stuff, like, share, comment, check them out. Have a good day. Alright, tell us something interesting.
Alright, well, today, January 3rd, we have a little bit of a goodie that I just happened to stumble across. Probably like to play with dates. And this is involving what's known as SL1, Stationary Low Power Reactor number 1. The United States Army was experimenting with nuclear reactors for cold weather situations. Now, this particular reactor was set up at the National Reactor Testing Station in Idaho, about 40 miles west of Idaho Falls, now known as the Idaho National Laboratory. Well, they were experimenting with popping out the control rods, and at 9:01 Mountain Standard Time, they had a little bit of an oops.
Uh-oh.
Well, small oops. Went promptly critical, and the intense heat generated an extreme water hammer, which propelled the reactor vessel to the roof of the reactor building. The operator, standing on top of the reactor lid, was pinned to the roof of the reactor building with expelled control rod shield plugs, while the reactor expelled water, debris, and fuel. The release of the materials hit 2 other operators, killing them, and the reactor vessel then fell down to its original position. Press reported that a steam explosion had killed all 3 of the military operators, and mentioned the reactor vessel plug. It remains now, to this date, the only U.S. reactor accident to cause immediate deaths. Now, when you think about reactor oops, call it, Um, the first the ones that come to mind, 3 Mile Island out in Pennsylvania. Think about Chernobyl, another great disaster. Yeah, bad pun.
Right.
Even the Fukushima accident caused by both a number of issues that happened. This was probably the grandfather of the mess. It happened back in 1961. Now, some of our details that's kind of interesting is that part of this program, this was an intentional plan that they had, was to heat small remote military facilities like the radar sites near the Arctic Circle and those in the dew line. This is an early warning. Design was for 3 megawatts of thermal power, but some tests would see megawatts of up to 4.7 performed in the months before the accident, while the operating power was 200 kilowatts electrical and 400 kilowatts thermal for space heating. Now, during the accident, the core power level reached nearly 20 gigawatts in just 4 milliseconds. That's some absolute speed. This direct cause was the over-withdrawal of the central control rod that absorbed neutrons in the reactor's core. The accident released about 80 curies of iodine-131, which was not considered significant due to its location in the remote higher desert of eastern Idaho. Not a lot of people living out there. About 1,100 curies of fissionable products were released into the atmosphere. That's the fun stuff that can go floating around. Now, this particular design originally came to light back in the 50s. From 1954 to 55, the Army was evaluating the need for nuclear reactor plants that would be operational in remote regions. And the reactors were to replace diesel generators and boilers that provided the electricity and space heating for the radar stations. The Army Reactors Branch wrote the guidelines for the project and hired the Argonne National Laboratory, or ANL, to design, build, and test a prototype reactor plant to be called the ALPR, Argonne Low Power Reactor. And some of the more important criteria, probably not involving blowing up, all components were to be transported by air, bring them in on a C-141, back then, Starlifter. All components limited to packages measuring 7.5 by 9 by 20 feet and weighing 20,000 pounds. It'd use standard components, minimum on-site construction, simplicity and reliability. Hey, anybody in the neighborhood could have their own reactor. Adaptable to the Arctic permafrost region, and a 3-year fuel operating lifetime per core loading. Now, the prototype was constructed at the National Reactor Testing Station from July of 1957 to July of 1958. Originally went online on August 11th, 1958, and became operational October 24th, formally dedicated on the 2nd of December 1958. Now, 3 megawatts thermal boiling water reactor used 93.20% of highly enriched uranium fuel. That's pretty good usage. It operated with natural circulation, using light water as a coolant versus heavy water, and moderator. Now, ANL used its experience from borax experiments to design the reactor. The circulating water system operated at 300 pounds per square inch, flowing through fuel plates of uranium aluminum alloy. The plant was turned over to the Army for training and operating experience in December of 1958 after extensive testing, with Combustion Engineering Incorporated acting as the lead contractor beginning in February 5th, 1959. Now, little note here, it says the CEI was responsible for the actual operation of the SL1 reactor for the routine training of military personnel and for developmental research programs. The contractor provided at the site a project manager, operations supervisor, test supervisor, a technical staff of approximately 6 personnel. In recent months, the project manager spent approximately half the time at the site and half the time at the contractor's office in Connecticut, all the way across the country. In his
That's a lot of
absence, huh?
That's a lot of halves.
That's a lot of halves. In his absence, either the operations supervisor or the test supervisor was assigned as project manager. It was understood, as indicated by testimony before the board, that the CEI would provide supervision on any shifts when non-routine work was carried out. The AEC's Idaho office and the Army Reactor's office clearly believed the addition of night supervisors when only routine work was involved would defeat the part of purpose of operating a reactor under the existing arrangement, i.e. to obtain plant operating experience with only military personnel. This is based off of a report from the SL1 incident, January 3rd, 1961. Now, trainees in the Army Reactor Training Program included members of the Army called cadre, who were the primary plant operators. Many maritime civilians also trained along with a few Air Force and Navy personnel. When the plant operation was generally done by the cadre and two-man crews, development of the reactor was supervised directly by CEI staff. CEI decided to perform development work on the reactor as recent as the latter half of 1960, which the reactor was operated at 4.7 megawatts thermal for a PL1 condenser test. As the reactor core aged and the boron-neutron poison strips corroded and flaked off, I don't see how this is going bad, CEI calculated that about 18% of the boron in the core had been lost. On November 11, 1960, CEI installed cadmium strips, also a poison, to several T-slots positioned to increase reactor shutdown margin. Interesting enough, it almost looks like a big garbage can. It says that the large cylindrical building holds a nuclear reactor embedded in gravel at the bottom, the main operating area or operating floor in the middle, and a condenser fan room near the top. Miscellaneous support and administration buildings surround it. Now, most of the plant equipment was a cylindrical steel reactor building known as the ARA 602, 38.5 feet in diameter with an overall height of 48 feet. It was made of plate steel, most of which had a thickness of 1/4 of an inch. Access to the building was provided by an ordinary door through an enclosed exterior stairwell, the support facilities building, and an emergency exit door led to an exterior stairwell at the ground level. The reactor building was not a pressure-type containment shell which had been used in reactors located in populated areas, again, 3 Mile Island. Nevertheless, the building was able to contain most of the radioactive particles released by the eventual explosion. Now, the reactor structure was built to hold 59 fuel assemblies, 1 startup neutron source assembly, and 9 control rods. The actual core in use had 40 fuel elements and was controlled by 5 cruciform rods. The 5 active rods were in the shape of a plus symbol in cross-section, 1 in the center, rod number 9, and 4 in the peripheral area on the active cores, rods 1, 3, 5, and 7. Control rods were made of 60 mils, 1.5 millimeter thick cadmium, clad with 80 mils of aluminum. They had an overall span of 14 inches and an effective length of 32 inches. The 40 fuel assemblies were composed of 9 fuel plates each. The plates were 120 mils thick, consisting of 50 mils of uranium-aluminum alloy meat covered by 35 mils of X8001 aluminum cladding. The meat was 25.8 inches long and 3.5 inches wide. The water gap between the fuel plates was 7.9 millimeters. Water channels within the control rod shrouds was 13 millimeters, and the initial loading of the 40 assembly core was highly enriched with 93.2% of uranium-235 and contained 31 pounds of U-235. Now, the deliberate choice of the smaller fuel-loading element made the region near the center more active than it would have been with the 59 fuel assemblies. The 4 outer control rods were not even used in the smaller core after tests concluded that they were not necessary. In the operating SL1 core, rods 2, 4, 6, and 8 were dummy rods, had newly installed cadmium shims, or were filled with test sensors, and were shaped like the capital letter T. The effort to minimize the size of the core gave rod 9 an abnormally large reactivity worth. Now, on that Tuesday, again, January the 3rd, 1961, SL1 was being prepared for a restart after a shutdown of 11 days over the holidays. Let's all blame Santa Claus. Maintenance procedures required that Rod 9 be manually withdrawn for a few inches to reconnect it to the drive mechanism. And again, 9:01 p.m. Mountain Standard Time, this rod suddenly was withdrawn too far, causing the SL1 to go into prompt critical instantly. 4 milliseconds. Go ahead, that's less than a second. Just boop. The heat generated by the resulting enormous power excursion caused the fuel inside the core to melt and to explosively vaporize. The expanding fuel produced an extreme pressure wave that blasted water upward, striking the top of the reactor vessel with a peak pressure of 10,000 pounds per square inch. This slug of water was propelled at 160 feet per second. That's some serious speed.
Right. Average
pressure of around 500 pounds per square inch, and caused what's known as the extreme water hammer, propelled the entire reactor vessel upward at 27 feet per second, while the shield plugs were ejected at 85 feet per second. With 6 holes at the top of the reactor vessel, high-pressure water and steam sprayed the entire room with radioactive debris from the damaged core. A later investigation concluded that the 26,000-pound vessel had jumped 9 feet 1 inch, parts of it striking the ceiling of the reactor building before settling back into its original location, depositing insulation and gravel on the operating floor. If the vessel's number 5 seal housing had not hit the overhead crane, it would have gone up about 10 feet. The excursion, steam explosion, and vessel took 2 to 4 seconds.
Oh, dear.
That would be a heck of a shock to, well,
right?
The 3 that were in there really got shocked. A spray of water and steam again knocked 2 operators onto the floor, killing one, severely injuring the other. The number 7 shield plug from the top of the reactor vessel impaled the 3rd man through his groin and exited his shoulder, pinning him to the ceiling. The victims listed as Army Specialist Richard Leroy McKinley, age 27, and John A. Burns, age 22, and Navy Seabee Construction Electrician First Class, CE1, Richard C. Legg, age 26. It was later established by author Todd Tucker that Burns, the reactor operator, had lifted the rod and caused the excursion. Legg, the ship supervisor, was standing on top of the reactor vessel and was impaled and pinned to the ceiling, and McKinley, the trainee, stood nearby. Only McKinley was found alive, unconscious, and in deep shock by rescuers. This was consistent with the analysis from the SL1 Board of Investigation, and with results of the autopsies which suggested that Burns and Legg died instantly, while McKinley showed signs of diffuse bleeding within his scalp, indicating he survived about 2 hours before succumbing to his wounds. All 3 of the men died of physical trauma.
Well then.
Now, early press reports indicated that the explosion may have been due to a chemical reaction, but that was shortly ruled out. Fast neutron activation had occurred by various materials in the room, indicating a nuclear power excursion, unlike a properly operating reactor. In a thermal neutron reactor, such as the SL1, neutrons are moderated or slowed down to control the nuclear fission process and increase the likelihood of fission with the U-235 fuel. Without a sufficient moderator, cores such as the SL1 would be unable to sustain a nuclear chain reaction. When the moderator was removed from the core, the chain reaction decreases. Water, when used as a moderator, is maintained under high pressure to keep it liquid. Steam formation in the channels around the nuclear fuel suppresses the chain reaction. Another control is the effect of the delayed neutrons on the chain reaction in the core. Most neutrons, the prompt neutrons, are produced nearly instantaneously by the fission. But a few, approximately 0.7% of the U-235 fueled reactor operating at a steady state, are produced through a relatively slow radioactive delay or decay of certain fission products. These fission products are trapped inside the fuel plates in close proximity to the uranium-235 fuel. The delayed production of the fraction of the neutrons enabled the reactor power changes to be controlled on a time scale amenable to humans and machinery. In the case of an ejected control assembly or poison, it is possible that the reactor to become critical on the prompt neutrons alone, i.e. prompt critical. When the reactor is prompt critical, the time to double the power is in the order of 10 microseconds. The duration is necessary for temperature to follow the power level depends on the design of the reactor core. Typically, the coolant temperature lags behind the power by 3 to 5 seconds in a conventional LWR. In the SL1 design, it was about 6 milliseconds before the steam formation started. Now, the SL1 was built with a main central control rod that can produce a very large excess reactivity if it was completely removed. The extra rod worth was in part due to the decision to load only 40 of the 59 fuel assemblies with nuclear fuel, thus making the prototype reactor more active in the center. The normal operation control rods were withdrawn only far enough to generate sufficient reactivity for a sustained nuclear reaction and power generation. In this accident, however, the additional reactivity was enough to take the reactor prompt critical within an estimated 4 milliseconds. This was too fast for the heat from the fuel to permeate the aluminum cladding and boil enough water to fully stop the power growth in all parts of the core via negative moderator temperature and void feedback. Now, the post-accident analysis concluded that the final control method, dissipation of the prompt critical state at the end of the sustained nuclear chain reaction, occurred by means of catastrophic core disassembly, destructive melting, vaporization, and the consequent conventional explosive expansion of the parts of the reactor core, where the greatest amount of heat was being produced most quickly. It was estimated that the core heating and vaporization process happened in about 7.5 milliseconds.
Wow.
That's cooking. Before enough steam had been formed to shut down the reaction, beating the steam shutdown by a few milliseconds. A key statistic makes it clear why the core blew apart. The reactor designed for a 3 megawatt power output momentarily at the peak of 20 gigawatts, a power density of over 6,000 times higher than the safe operating limit. Woo! This criticality accident is estimated to have produced 4.4 times 10 to the 18th fissions.
That's too much math.
Or about 133 megajoules, or 32 kilograms of TNT energy. Now, after the power excursion, heat sensors above the reactor set off alarm in the NRTS security facility. At the time of the accident, false alarms had occurred in the morning and afternoon of the same day. The response team of 6 firemen, Ken Durden, assistant chief.
Seems a little lacking.
A little late, yeah. This happened at, early in the day, middle of the day. At the end, it finally happened again. But they sent out Ken Darden, assistant chief, Mel Hess, lieutenant, Bob Archer, Carl Johnson, Egon Lamprecht, Gerald Stewart, and Vern Conlon arrived 9 minutes later expecting another false alarm. Guys, I don't think that's a false alarm. They noticed nothing unusual at first, with only a little steam rising from the building, normal for the cold night. It was 6 degrees Fahrenheit. The firefighters, unable to hail anyone inside the facility, had a security guard open a gate for them. They donned the Scott air packs, arrived at the support facility building to investigate. While the building appeared normal, but nothing was unoccupied. 3 mugs of warm coffee were in the break room, and 3 jackets were hanging nearby.
Well then.
They entered the reactor control room and noticed a radiation warning light. Their handheld radiation detector jumped sharply above its maximum range as they were climbing the stairs to the reactor's operating floor level. This prompted a retreat for the second radiation detector. The second radiation detector also maxed out at 200 roentgens per hour as they ascended again. They peered into the reactor room before withdrawing. At 9:17, 16 minutes after the explosion, a health physicist arrived. He and the assistant chief, Moschberger, both wearing air tanks and masks with positive pressure in the mask to force out any potential contaminants, approached the building's stairs. Their detectors read 25 roentgens per hour as they started up the stairs, and they withdrew. Finding higher scale ion chamber detector, the pair reached the top of the stairs to look inside the reactor room for the 3 missing men. Their Jordan Radector AG 500 meter pegged at 500 roentgens per hour on the way up.
Wow.
Yeah, they saw a dim, humid, wet operating floor strewn with rocks and steel punchings, twisted metal, and debris scattered. Coming from nearby Idaho Falls, the lead SL1 health physicist, Ed Valario, and Paul Duckworth, the SL1 operations supervisor, arrived around 10:30 p.m. They donned air packs and went quickly to the administration building, through the support building, and up the stairs to reach the reactor floor. Halfway up the stairs, Valario heard McKinley moaning. Finding him and the second operator on the floor, who appeared to be dead, the two decided to return to the checkpoint to get help for the bleeding McKinley. The two were joined by 3 health physicists who donned air packs and went with them back to the reactor floor. Masks on their air packs were fogging up, limiting visibility. McKinley was moving slightly, but his body was partially covered with metal debris, which the rescuers had to remove in order to carry him with a stretcher. Valerio also moved debris in an attempt to find the missing crewman. Burns was partially covered with steel pellets and blood. Another man checked for Burns' pulse and announced that he was dead. The 3 men attempted to move McKinley via the outside stairs, sending one man outside to meet them with a truck, but after carrying McKinley across the operating floor to the exit, they discovered equipment blocking the emergency exit door. This forced the rescuers to reverse course and use the main stairs. During the movement of McKinley, 2 of the men had their Scott air packs freeze up and cease to work. Duckworth evacuated due to the malfunction, while Valario removed his mask and breathed contaminated air to complete the evacuation of McKinley. The rescue took about 3 minutes.
Wow.
The evacuation of McKinley quickly turned into a major radiological problem. McKinley was first shuttled back into a panel truck and then into the back of an ambulance. The on-call nurse, Helen Lyson, tending to the patient at the back of the ambulance, heard at least a faint breath, perhaps his last. But before the vehicle made it into the nearby Highway 20, the AEC doctor had the nurse evacuated and entering the ambulance found no pulse. He pronounced the man dead at 11:14 p.m. The contaminated ambulance with the body of McKinley was driven out into the desert and abandoned for several hours.
Wow.
Now, 4 men had entered the reactor building at 10:38 and found the 3rd man. Leg was discovered last because he was pinned to the ceiling above the reactor by a shield plug and not easily recognizable. Now, extensive decontamination was conducted that night. About 30 of the first responders took showers, scrubbed their hands with potassium permanganate, and changed their clothes. The body in the ambulance was later disrobed and returned to the ambulance, which took it to a nearby facility for storage and autopsy. On the night of the January the 4th, a team of 6 volunteers worked in pairs to recover Burns' body from the SL1 operating floor. It was taken also by ambulance to the same facility. After 4 days of planning, the 3rd body, by far the most contaminated, was retrieved. Modifications to the reactor room had to be performed by a welder inside a lead-shielded box attached to a crane.
Well then.
That's creative. On January 9th, the relays at 2 at a time, the team of 10 men, allowed no more than 65 seconds exposure each, used sharp hooks on the end of long poles to pull Leg's body free of the number 7 shield plug, dropping it into a 5 by 20 foot stretcher attached to a crane outside the building. Now, radioactive copper, or Cu-62 from a cigarette lighter screw on McKinley and a brass watch buckle from Burns, both proved that the reactor had indeed gone prompt critical. This confirmed with several other readings, including gold from Leg's wedding ring. Nuclear accident dosimeters inside the reactor plant and particles of uranium from the victim's clothes also provided evidence of the excursion. Before the discoveries of neutron-activated elements in these men's belongings, scientists had doubted the nuclear excursion had occurred, believing the reactor was inherently safe.
Yeah, that's funny.
Strontium-91, a major fissionable product, was also found with the uranium particles. These findings ruled out early speculation that a chemical explosion had caused the accident. Now, some sources and eyewitnesses' accounts confuse the names and positions of each victim. In Idaho Falls, the unknown story of America's first nuclear accident, the author indicates that the rescue teams identified Burns as the man found still alive, believing that Legg's body was the one found next to the reactor shield recovered that night after the accident, and that McKinley was impaled by the control rod to the ceiling directly above the reactor. This misidentification, caused by several blast injuries to the victims, was rectified during autopsies conducted by Clarence Lushbaugh, but this caused confusion for some time. The 7 rescuers who carried McKinley and received Carnegie Hero Awards from the Carnegie Hero Fund were Paul Duckworth, the SL1 Operations Supervisor, Sidney Cohen, SL1 Test Supervisor, William Rausch, SL1 Assistant Operations Supervisor, Ed Valario, SL1 Health Physicist, William Gamel, the on-duty AEC Site Survey Chief, Lavelle J. Callister, the Health Physicist, and Delos E. Richards, Health Physics Technician. Now, one of the main required maintenance procedures called for Rod 9 to be manually withdrawn about 4 inches, or 10 centimeters, in order to attach it to an automated control mechanism from which it had been disconnected. Now, post-accident calculations, as well as the examination of scratches on Rod 9, estimated that it actually had been withdrawn about 20 inches.
Oh.
Yeah, causing the reactor to go prompt critical and triggering that steam explosion. The most common theories proposed by withdrawal of the rods was sabotage or suicide by one of the operators, murder-suicide involving, that's just crazy, inadvertent withdrawal of the main control rod, or an intentional attempt to exercise the rod to make it travel more smoothly within its sheath. The maintenance logs do not address what the technicians were attempting to do, and thus the actual cause of the accident will never be known. However, it seems very unlikely that it was a suicide. Post-accident experiments were conducted with identically weighted mock control rod to determine whether it was possible or feasible for 1 or 2 men to have withdrawn the rod by 20 inches. Experiments included a simulation of the possibility that a 48-pound central rod was stuck and one man freed it himself, reproducing the scenario that investigators considered the best explanation. Burns broke the control rod loose and withdrew it accidentally, killing all 3 men. When testing the theory that Rod 9 was rapidly withdrawn, the 3 men took part in time trials, and their efforts were compared to the energy of the nuclear excursion that occurred. Now, a quick rundown on the accident report. The spare SL1 control rod actuator assembly that was used in the mock-up on the speed of manual rod withdrawal was measured for several subjects. The equipment is the same as that of the SL1, except the control rod, which is simulated by weight to give a total movable load of 84 pounds, the net weight of the movable assembly in water. The test was conducted by instructing the subject to lift the rod as rapidly as possible, while an electric timer measured the elapsed time from the beginning of rod motion to the predetermined distance of withdrawal. Distances up to 30 inches were measured. The above reasoning indicates that the required rate of rod withdrawal to produce a period of short of 5.3 milliseconds is well within the limits of human capability. That was the interim report on May 15th, 1961. Now, at SL1, control rods would sometimes get stuck in the control rod channel. Not very reassuring, kids. Numerous procedures were conducted to evaluate control rods to ensure they were operating properly. They were rod drop tests and scram tests of each rod, in addition to periodic rods exercising and rod withdrawals for normal operation. From February 1959 to November 18, 1960, this is unreassuring. There were 40 cases of stuck control rods for scram and rod drop tests of about 2.5% failure rate. From November 18th to December 23rd of 1960, there was a dramatic increase in stuck rods, with 23 in that time period and a 13% failure rate. Besides these test failures, there was additional 21 rod sticking incidents from February 59 to December of 1960. 4 of these had occurred in the last month of operation during routine rod withdrawal. Rod 9 had the best operational performance record, even though it was operated more frequently than any other rods. Now, rod sticking had been attributed to misalignment, corrosion product buildup, bearing wear, clutch wear, drive mechanism seal wear. Many of these failure modes were caused by a stuck rod during tests, like bearing and clutch wear would apply only to movement performed by the control rod drive mechanism. Since the 9 rod is centrally located, its alignment might have been better than the 1, 3, 5, or 7, which were more prone to sticking. After the accident, logbooks and former plant operators were consulted to determine if there had been any rods stuck during the reassembly operation that Burns was performing. One person had performed this about 300 times, another 250 times. Neither had ever felt a control rod stick was being manually raised during the procedure. Furthermore, no one had ever reported a stuck rod during manual reconnection. During the congressional hearings in June 1961, the SL1 project manager, W.B. Allred, admitted that the lack of supervision by CEI of the SL1 plant operation on an around-the-clock basis was because the Atomic Energy Commission had rejected the idea for budget reasons. Yay!
Budget!
Let's save money and kill people. Now, Allred was also grilled on the matter of increased rod sticking between November 16th, 1960, and the final shutdown of December 23rd. Of the increase, Allred stated, "I was not completely aware of the significant increase, and I was not aware of the sharp increase had occurred." When asked who the person was responsible for informing him of the sticking problem, Allred said that Paul Duckworth, the operations supervisor, should have reported this to him but did not. Let's pass the buck.
Not me.
Not me. When pressed, Allred said that if he had known that the increased control rod sticking, he would have shut the plant down for more detailed examination. And the note here says the mechanical material evidence combined with the nuclear and chemical evidence forced them to believe that the central control rod had been withdrawn very rapidly. The scientists questioned the former operators of SL1, "Did you know that the reactor would go critical if the central rod was removed?" Answer, of course. We often talked about what we would do if we were at a radar station and the Russians came. We'd yank it out. This is a quote from Susan M. Stacy, Proving the Principle, 2000. Now, consequences, always going to be something. The accident caused the design to be abandoned and future reactors to be designed so they single control rod removal could not produce a very large excess reactivity. Today, this is known as the once stuck rod criterion and requires complete shutdown capability even with the most reactive rod stuck in the fully withdrawn position. This documentation and procedures required for operating nuclear reactors expanded substantially and became more formal. Procedures had been previously taken 2 pages, expanded to hundreds. Radiation meters were changed to allow higher ranges for emergency response activities. Although portions of the center of the core had vaporized briefly, very little corium was recovered. The fuel plates showed signs of catastrophic destruction, leaving voids, but no appreciable amount of glazed molten material was recovered or observed. Additionally, there was no evidence of molten material having flowed out between the plates. It is believed that the rapid cooling of the core was responsible for the small amount of molten material. There was insufficient heat generated for any corium to reach or penetrate the bottom of the reactor vessel. So what happened with they call it the China syndrome, never had a chance to actually happen at SL1. Now, the SL1 reactor building contained most of the radioactivity, but iodine-131 levels on plant buildings downwind reached 50 times background levels during several days of monitoring. Radiation surveys on the support facilities buildings, for example, indicated high contamination in halls, but light contamination in offices. Radiation exposure limits before the accident were 100 retrogens to save a life and 25 to save valuable property. During the response to the accident, 22 people received doses of 3 to 27 retrogens for full body exposure. Removal of radioactive waste and disposal of the 3 bodies eventually exposed 790 people to harmful levels of radiation, and by March of 1962, the AEC awarded a certificate of heroism to 32 participants in the response. Now, after a pause of evaluation of procedures, the Army continued its use of reactors, operating the Mobile Low Power Reactor ML1, which started full power operation in February 28th of 1963, becoming the smallest nuclear reactor plant on record to do so. This design was eventually abandoned after corrosion problems.
What?
While the tests had shown that nuclear power was likely to have lower total costs, the financial pressures of the Vietnam War caused the Army to favor lower initial costs and stop the development of the reactor program in 1965, although the existing reactors continued operating until 1977, the MH-1A. Now, General Electric was hired to remove the reactor vessel, dismantle, and clean up the contaminated buildings at the project site. The site was cleaned from 61 to 62, removing the bolt of contaminated debris and burying it. Let's throw it in the ground, kids. Removing the bulk of contaminated supply, the massive cleanup operation included the transport of the reactor vessel to a nearby hot shop for extensive analysis. Other items of less importance were disposed of or transported to decontamination sites for different kinds of cleanup. About 475 people took part in this cleanup, including volunteers from the U.S. Army and the Atomic Energy Commission. How'd you like to volunteer for that? You guys want to go glow in the dark, don't you?
Thank you.
The recovery operation included cleaning of the operating room floor of radioactive debris, the extremely high radiation area surrounding the reactor vessel, and the fan room directly above it, contributed to the difficulty of recovering the reactor vessel. Remotely operated equipment, cranes, boom trucks, and safety precautions had to be developed and tested by the recovery team. Radiation surveys and photographic analysis was used to determine what items needed to be removed from the building first. Powerful vacuum cleaners, operated manually by teams of men, collected vast quantities of debris. The manual overhead crane above the operation floor was moved numerous heavy objects weighing up to 19,600 pounds for them to be dumped out on the ground outside. Hot spots where up to 400 retrojoules per hour were discovered and removed in the work area. Well, while the operating room floor was relatively clean and radiation fields manageable, the manual overhead crane was employed to do a trial lift of the reactor vessel. The crane was lifted with a dial-type load indicator, and the vessel was lifted a few inches. The successful test found that an estimated 23,000 pounds vessel, plus an unknown amount of debris weighing 26,000 pounds, after removing a large amount of the building structure above the reactor vessel, a 60-ton Manitowoc Model 3900 crane lifted the vessel out of the building into an awaiting transport cask attached to a tractor-trailer combination with a low-boy 60-ton capacity trailer. After raising or removing 45 power lines, phone lines, and guy wires from the proposed roadway, the tractor-trailer, accompanied by numerous observers and supervisors, proceeded about 10 miles an hour to the ANP hot shop, originally associated with Aircraft Nuclear Propulsion Program, located in a remote area of the NRTS known as Test Area North, about 35 miles away. A burial ground was constructed about 1,600 feet northeast of the original site of the reactor. It was opened on May 21st, 1961, and burial of the waste helped minimize radiation exposure to the public, and site workers would have resulted from transport of contaminated debris from SL1 to the radioactive waste management complex over 16 miles of public highway. The original cleanup of the site took 24 months. The entire reactor building, contaminated materials from nearby buildings, and the soil and gravel contaminated during cleanup were buried in the burial ground. The majority of the buried material consists of soils and gravel.
They buried soil underground.
Yeah, the radioactive was buried by regular soil.
I would say they buried dirt with dirt.
Exactly. What a dirty job. Now, recovered portions of the reactor core, including the fuel and other parts of the reactor, were important to the accident investigations, were taken to the hot shop for study. After the accident investigation was complete, the reactor fuel was sent to the Idaho Chemical Processing Plant for reprocessing. The reactor core, minus the fuel, along with the other components sent to the hot shop for study, was eventually disposed of by the Radioactive Waste Management Complex. Now, the remains of SL1 are now buried near the original site. The burial site consists of 3 excavations with a total volume of 99,000 cubic feet of contaminated material being deposited. The excavations were dug as close to basalt as the equipment would allow and ranges from 8 to 14 feet in depth. At least 2 feet of clean backfill was placed over each excavation. Shallow mounds of soil over the excavations were added and the complete cleanup activities in September of 1962. The site and burial mound are collectively known as United States Environmental Protection Agency Superfund Operational Unit 5-05. Now, numerous radiation surveys and cleanup of the surface of burial ground and surrounding area have performed in the years since the SL1 accident. Aerial surveys were performed by the EG&G Las Vegas in 1974, 82, 1990, and 93. The Radiological Environmental Sciences Laboratory conducted gamma radiation surveys every 3 to 4 years between 73 and 87, and every year between 87 and 94. Particle picking at the site was performed in 1985 and 1993, and results from the surveys indicated that cesium-137 and its progeny, or decay products, are the primary surface soil contaminants. During a study of surface soil in June of 1994, hotspots, or areas of higher radioactivity, were found within the burial ground within activities ranging from 0.1 to 50 milliretrogens per hour. On November 17, 1994, the highest radiation reading ever measured at 2.5 feet above the surface was 0.5 milliretrogens per hour. The local background radiation was 0.2 milliretrogens per hour. The 1995 assessment by the EPA recommended that a cap be placed over the burial mounds. The primary remedy for the SL1 was to be contaminated by capping with an engineered barrier constructed primarily of native materials. This remedial action was completed in 2000 and first reviewed by the EPA in 2003. But that pretty much rounds up our scientific oops from 1961. This has been the Bearded Historian. You folks have a good Happy New Year to you.
Good night.